Hello friends, myself Narendra Patil, and today I am going to present this video for time series analysis using R software. Before going to start this video, I just want to say or to answer about two simple questions related to this title: time series and R. Why time series? Because time series is one of the most statistical technique which is widely used in industrial sector or any government sector, and it is based on any real-time or time-based data sets. And R, because R is specifically or basically designed for statistical purpose in order to visualization of the data or analysis of the data sets. So before going to start analysis or real analysis of any real life data sets, we are going to see some basic concepts or theoretical concepts related to time series. Let's see first what is time series. A time series is a series of data points indexed or listed or a graph with respect to time or the data set which are related to or recorded on a specific time or in an equal interval of time. It is a sequence of observations which is taken at a particular time interval, and the time series analysis is the collection of data at specific interval over a period of time with the purpose of identifying the trends, cycles, or the seasonal variances, and to add the forecasting of the future event. That's what, in order to predict the futures, we have to understand the pattern of the data sets or the record or the observations which are recorded on a particular point of time. So, generally, we can observe there are three types of variations in any particular data set which are related to time. So first one is seasonal variation, which is repeated over a specific period of time, like rainfall. Uh, Rainfall in India for it is in June to September, which is rainy season. Uh, Also, we can see temperature in May or June month. So simply, these are the seasonal types. Like gold will sell maximum. Gold has maximum sale in Deepavali. This is just an example of seasonal variation. Similarly, trend variation that moves up or down is and cyclic variation. These are the three types of variation you can basically observe in time series data sets or the pattern of the data. The time series analysis is used in order to understand the underlying structure and function that produce the observations. Understanding the mechanism of time series allows a model to develop that explains the data in such a way that we can predict, monitor, or can control the data sets. There are two basic plots in time series analysis, which first one is ACF and PSF. ACF means autocorrelation function and PSF means partial autocorrelation function. When we calculate simple correlation between two variables, it just measures the linear relationship between two variables. But autocorrelation measures the linear relationship between the lag values of time series. What is lag values? Lag values is the difference between the two values of which we are going to calculate autocorrelation. That is what, suppose x1, x2, xn is your sample of random observations. So x of t is the tth observation and x of t minus 1 is the t minus 1th observation. Then the correlation between x of t, covariance between x of t minus x of t minus 1 is the autocorrelation between x of t minus, comma x of t minus 1, or the tth observation comma t minus 1th observation. And the difference between the lag number of observations, tth number of observation is the lag value. That is what, suppose we are going to take covariance between 10th observation and 9th observation, then 10 minus 1, which is 10 minus 9 is, which is equal to 1, so it is 1 lag value, and so on. ACF of trended time series tend to have a positive value and that slowly decreases as the lag increases. This will again explain when we saw actual ACF plot. That is what, if your dataset has a trend only, then you can see the decay in the as each lag increases, the times ACF plots also will show you the decreasing trend in the spike of the plot. When data are seasonal, then the autocorrelations will be larger for the seasonal lags. So it will show you some zigzag pattern, some increment, decrement, increment, decrement, and it will also, as H increases or lag difference increases, it will also go to decreases. When the data are both the trend and seasonal, you will see the combination of these effects. And partial autocorrelation function gives the partial correlation of stationary time series with its own lag values. Regress the values of the time series all other short legs when other are kept to be as a constant. R as a basic command to plot ACF and PSF as their names, so there is nothing to do other things to plot the ACF and PSF. So before going to model any data set, or before going to see uh, or before going to analysis of series or time series analysis, we have to see whether the process is stationarity or not, and whether the residuals are noise, IID noise or white noise or not. So what is stationarity? Stationarity means that the statistical property of the process or the time series which do not change with respect to time. That is what its behavior should be a constant for over a period of time. It's called stationarity. And why stationarity is important? Because many useful tools and statistical tools are depends on it. And that the series of observation which independent and identically distributed with mean close to zero and constant variance with respect to time. That is what, as time changes, variance should not be going to change with respect to time, and mean should be around to close to zero, not exactly zero. Of course, they will not exactly equal to zero as there is some random variation for a white noise series. We expect at least 95% of the spike in ACF will lie within plus minus 2 per 2 upon square root of n, where n is the length of the time series. So plus minus 2 upon root n is the control limits for ACF, and it is a common plot to this bound. It is common to plot these bounds on a graph of the ACF, the blue dashed line which you will saw in the plots. So there are basic steps to modeling any data set. First step is to visualize the time series data set in order to check the trend or any seasonality pattern of the data set. The visualization is important. Second step is to check stationarity of the process. If the process is stationarity, that is what behavior is not changing with respect to time, then it's easy to predict the future, and it's predict future with minimum variation. So stationarity is important. So second step is to check stationarity, and what happen if process is not stationarity, then how to convert the non-stationarity into stationarity, we will see in example. Find optimal parameters, of course, which model we are going to fit, we have to optimate parameters, then build a ARIMA model, and on the basis of the model we can predict future. So let's start with example and see how actually we can build a model. So this is our software, and we are going to see how to actually predict the model. Let's start. uh, I, I have imported the data set which is already stored in our software, which is air passenger data set. So let's see what is actual data is. So see, there is a set of observations from 1949 to 1960, and for each year there are 12 observations for each month, which are number of air passengers which travels in a month through airlines. So primary visualization, let's see. First we summarize the data, in which minimum value is 104 observations, that is 104 air passengers is the minimum value. 180 is the first quarter, 265.5 is the median. Okay, these are the basic statistics, descriptive statistics, which I am not going to explain in details. Let's see the nature of the data set. Let me zoom it out. So now you can see there is it is easily observed, you can easily observe that it is increasing. So of course it is trend, and during each year there are some fluctuations in air passengers. So let's see here, this is 1949, and January, February, March, April, May, June, July, August, September, October, November, and December. So basically there is increment in July and August. So, and let's see, again decrement, again increment, again decrement, increment, decrement. So basically what we can observe, let's again see here, 1949, January, February, March, April, May, June, July, and August. Again July and August. Similarly you can observe here July, August, or January, February, March, April, May, June, July, August. So for each year you can observe there are number of maximum number of passengers for increment in the number of passengers in July, August, and September. So it is trend, as well as we can say that it is also seasonality, because uh, there are a number of increase in every year the number of passengers are increases in this month of period. So let's see the trend line we can add. So we can basically observe it is increasing trend line, and it is of course as your number of years are going to increase, the number of air passengers are also going to be increased. Cycle, every year there are 12 observations, and again after 12 observations are completed, this cycle is repeated for each year. In order to see in which okay, this is a mean plot. I'm going to explain this mean plot after some time, when we will see the mean plot of the residuals. So let's skip this. So what is this? This is a box plot for each month in each year number of observations. So you can see in January, uh, this is January number of air passengers, this is February number of passengers, this is March, April, May, June, July, and August. So you can observe here again in July and August there are number of maximum passengers. So see, from 5th means May, June, July, and August there is increment of passengers, and again there is decrement of passengers. So we can also found some seasonality in the data set. Now let's see some basic plots, which is ACF. Now so ACF again shows that there is trend and seasonality. Suppose there is only the trend, then these spikes are only as a straightforward, which is not this type of zigzag. So it shows that as per our definition, as we saw, this is somehow decrement, again increment in cyclic pattern. So it will show you that there is some seasonality pattern, and of course ACF again shows the process is non-stationary. Similarly we can observe from PSAF. So these blue lines are the confidence band that we have discussed earlier. So now we already saw that our process is non-stationary. Now our object is to how to transfer non-stationary process into the stationarity. So basically there are we can normally use two types of transformations to transform non-stationary process into the stationarity. First one is to log transformation, and second one is differentiation. So let's see, we can begin first our initial plot. Just focus on this plot, and first I am going to take log transformation and just observe what actually the changes are happening. So you can see some pattern is going to be changed, but again this is not constant with respect to time, so it is going to be again non-stationary. Let's see, check with differentiation. Oh, the mean is actually close to 0, but process is again not stationary because variance is going to be changed with respect to time. And my objective is to become stationary. The variance is also with respect constant with respect to time. Let's try with again differentiation this process. Again, it is variance is not constant over the time. Okay, now I am not going to take again differentiation. I will use log data with differentiation. So let's see. Wow, that's great. We can now find that our mean of the process is closely around to 0, and variance is again constant with respect to time, we can now say that the process becomes stationary. So if we saw the line from 0, the mean is around 0, which is close to 0, and the pattern will be around, pattern is also going to be seem to be same. So we can also say that variance is constant with respect to time. Now before going to model or forecast, I need two libraries, which is T series and forecast. Forecast is already available in my in R software, so it's not needed to download. And if you don't have T series or any package to in your R software, then you can easily install by install.package, or you can also go here in packages and you can install it. So uh, so let's start to model. We have already tested our time series. Now in our software, you don't need to do the transformations, you don't need to check, you don't need to take any log, any differentiation. You just need to enter auto.arima, and you can just check which is the best fitted model for your data set. Now what auto.arima can do: auto.arima can check whether your process is stationary or non-stationary, whether there is any trend or seasonality, and it will transfer your non-stationary process into the stationarity by transformations that we have done in previous. So auto.arima does not allow us to do that process, it will do automatically. Let's start and observe how actually auto.arima can fit the model. Let's observe how auto.arima is going to change the parameters, and it will fix when it realizes that this is the best fitted model with minimum variation, and auto.arima will start to modeling. It's still running and checking. Okay, the best model is 211010 and 12. Okay, before going to discuss this model, I would like to explain again this. I I told you that mean should be close around to 0, and before this I I told you about one plot of mean of aggregate mean of each value. In this mean plot, we can observe mean going to be changed with respect to time, which is increasing. That's why it also shows that the process is stationary, and our objective is mean should be constant over or fixed with respect to time. So this plot again shows that the process is non-stationary. So we already fit the model. Before going to analyze or predict, I just want to explain this model, what this model actually shows. The best fitted model for we is ARIMA 211010. So what is this 2? This is P parameter. ARIMA PDQ. ARIMA, I will type here. What is ARIMA? ARIMA has a 3 parameters, which is P, D, and Q. And what is this PDQ? P stands for AR process, ARP parameters, D stands for differentiation, and Q stands for MA process. So the P and Q are the parameters of AR and MA process respectively, and D is the differentiation operator, how much time we have differentiate our data set in order to transform non-stationarity into the stationarity. And what is the second parameter? It is again PDQ, and this one stands for seasonality parameter. So as we have already observed, our data set also have a seasonality. Now we have fit the model. Let's start with some summarization again the model. So with summary of this fitted model, we saw that we have the parameters values, which is AR1, AR2, and MA1. So there are three parameters. AR2 AR process has two parameters, which is AR1, AR2, and MA1 for MA process one parameter. So this is sigma square estimated as 132.3 log likelihood estimated, and AIC, AICC, and BIC. These are the parameters of the time series model, which we consider while comparing one model with another model. So what is AIC? AIC is ACAC information criteria, which is you can also read this section in stochastic process Sheldon books by Sheldon, or time series book by Montgomery. You can easily observe, easily found this criteria, ACAC information criteria, or which is also called as minimum AIC. So summary, apart from, we check residuals, and in the residual we can check whether our model is good fitted or not, and how to check this. Let's see. Before going to explain this graph, let's see L-Jung box test. L-Jung box test has the null hypothesis the model is not good fitted, and or the residuals are not IID. But as we saw, our p-value is less than 5% of level of significance, so we can reject null hypothesis. That is what we are accepting our alternative hypothesis, which is the noise are IID. What is meant by IID? Independent and identically distributed. So let's see. In the residual plot, we can observe the residuals are the mean of the residual is close to 0, and the variance is constant again with respect to time. So again, ACF shows that there are maximum at each lag differences increases, the maximum spikes are within the band, which is 2 upon root n, plus minus 2 upon root n, which is shown by blue lines. And we can neglect 5% of spikes, which if they cross blue lines. Again, histogram shows the residuals are normally distributed. So again, all the assumptions related to residual test are satisfied. Then so we can say that our fit model is good fitted. So based on this fitted model, which is good fitted, we are going to forecast future 10 years. So based on this, we just use forecast command to forecast the future values, and let's see whether our forecasted value has accept the pattern of the previous data sets or not, or whether it's correctly identified the pattern or not by plotting the forecasted value. Okay, now we can observe whatever we have previous pattern based on the previous data set. Our forecasted values are observed the same pattern, same trend, and forecasted the future value with great accuracy, because our model has identified the nature of the previous data set. So is that again good fitted? No. Before going to say that we are good fitted, we are going to test whether our model is good fitted or not. So the testing of the model. So in testing, what I did, I have a data set from 1949 to 1960. So I just exclude 1960 year and create new test data, which is from only 1949 to 1959. Okay, and model I have already fitted, just use and naming them model 2 by using the same parameter, or we can also use the as fitted model, but I have just pick that parameters from the fitted model, and I can simulate the ARIMA process. Okay, and predict again using the model fitted based on this test data prediction. And now I am going to see how much variation, or what are the actual values and what are the fitted values. Now let's see, and we can easily observe that. Okay, let me clear this, and we'll run again so we can easily observe. Now the second row shows you the actual value. These are the actual value in row 2, and in row 1 are the predicted value. So actual value in 1960 was 417 and predicted value is 425. Actual value in February or second month is 391 and predicted value is 409. 419, 472, 461, 462, 472, 486, 535, 538. It shows that we are very close to actual value. So based on this prediction and based on this test data, the prediction shows that our fitted model is good fitted. So that's it about time series analysis and how to fit the time series model. That's all. I really thanks to all to show this video from minus infinity to plus infinity.